Hey guys, so it was requested that I go over Hardy-Weinberg, so I figured that I would go real quickly and just do a quick little session on what Hardy-Weinberg says, what are the conditions, and then I'm going to do 3 different practice problems because these kind of problems are a little complicated and there's 2 different ways to solve them. So I wanted to go over and show you guys how I do these problems and just to kind of give you a little bit of help on this aspect. So Hardy-Weinberg is basically stating that if these conditions are met, then the population will not evolve. So this is a completely theoretical thing. So there's 5 different conditions that need to be met, and if these conditions are not met, then the population is going to evolve. And so I recommend that if you need a visual of this, you go to YouTube and look up, it's a TED Ed video. It's called The 5 Fingers of Evolution. You're going to notice that the voice on it is Paul Anderson, the gentleman who runs Bozeman Biology. And actually, Bozeman Science, he does he does chemistry, physics, he actually does a lot of things. So The 5 Fingers of Evolution, really easy to go with, okay? So the first thing, you think about your pinky finger. Your pinky finger is small, okay? So what we need with Hardy-Weinberg is we need extremely large population, like large population. So extremely large population is a requirement for Hardy-Weinberg. The second thing, whenever you think of it, actually, this isn't working so well because I'm not wearing my wedding band right now, but your ring finger traditionally means kind of think about marriage and whatnot. And so you need to have random mating. Okay, so we need to have random mating. You can't be selecting for certain traits and having any type of sexual selection. So random mating. The third thing is your middle finger, kind of gives you an M. And so that tells you that you can have no mutations. So we can't have any new alleles joining the population. So it's all no mutations. And then the fourth thing has to do with that we can have no gene flow. So you can't have any individuals entering your population or leaving your population. So no gene flow. And the fifth one has to do with no natural selection. There could be no trait that is more favorable or less favorable. Now, again, if you need a little bit of visual of this, it's a great TED video. It's a TED Ed. Go to YouTube and search The 5 Fingers of Evolution. It'll go through the 5 different aspects of Hardy-Weinberg. So again, you need to have extremely large population. You need to have random mating. You need to have no mutations, you need to have no gene flow, and then, of course, no natural selection. So I'm going to flip my camera real fast, and I'm going to kind of walk through some of the math with you guys, because that's what was requested was, hey, can you go over the math and how to do these? So let me flip my camera real fast and hijack my screen a little bit. And I actually am, my camera is flipped, so I can't see anything you're typing. I will look at it in a second, but it's kind of, honestly, I don't know if you can see it, but there's a bunch of cans. I'm like trying to balance it on top of cans. Yay. Okay. So again, you need to have a large population size. You need to have random mating, no mutations, no gene flow, and no natural selection. And so what that's telling us is if these conditions are met, then the population is not going to evolve. You will not see any changes in your allele frequency, and you will not see any changes in your genotypic frequency. Okay. And so there's a couple different things that we're going to have in the equation. Okay. The first thing we have is a P and a Q. Our P is going to stand for the frequency of our dominant allele. Our Q is going to stand for the frequency of our recessive allele. P squared is going to be our homozygous dominant, or the frequency of our homozygous dominant. 2PQ is the frequency of our heterozygous. And then Q squared is the frequency of our homozygous recessive. And so the way that I tell my students is that when you're looking at P and Q, you're looking at one allele. So we're looking at the frequency of the dominant allele, the frequency of the recessive allele. We're looking at one allele. Versus whenever you're looking at any of these, you've got a 2 there. P squared, 2PQ, and Q squared. There's a 2 in all of those, which tells you you're looking at a genotype. I'm looking at the individual and the fact that they are homozygous dominant. They have 2 of the dominant alleles. I'm looking at the individual. They have 1 dominant and 1 recessive allele. Again, they have 2 alleles. And then Q squared, we're looking at homozygous recessive. They have 2 recessive alleles. So whenever we're looking at just the single allele, you're just going to have a single P or a single Q. If you're looking at a genotype that requires 2 alleles because of it being diploid, you'll see a 2, P squared, 2PQ, or Q squared. And so when we look at these formulas, and I ran out of yellow paper, we're going to see that if you take the frequency of the dominant allele and the frequency of the recessive allele, and you add those together, you're going to get 1. And then if we take our frequency of our homozygous dominant, heterozygous, and homozygous recessive, that's also going to give us 1. So these are 2 equations that are very important that we remember. This is your Hardy-Weinberg equilibrium equation, okay? So I have a couple practice problems that I was going to do with you guys and hope that they can show up on the screen. It says within a population of butterflies, the color brown is dominant over the color white, and 40% of the butterflies are white. Given this information, calculate all the values, okay? So I like to use this chart. I make a P, I make a Q, I make a P squared, I make a 2PQ, and I make a Q squared, okay? And so when I do this, I'm gonna fill in what I know, okay? And now you always wanna start with Q squared. Q squared is always where you wanna start because of the fact that if I tell you how many have the dominant trait, you don't know whether that's P squared or 2PQ. So you have to start with Q squared always. Well, this question gave it to us. So 40% was white, and white is our recessive trait. So I'm gonna put 0.40 here. So if I know my Q squared, there's a value on here that I can solve. Q squared, to get to Q, you're going to take the square root of our Q squared, which gives us Q. Now, a lot of times students fall into a trap here. You see that 4 and you go, oh, the square root of 4 is 2. But very careful with decimals. It actually isn't 2. It's actually 0.63. And so we looked before and we said that P plus Q equals 1. So if I know his Q is 0.63, then I can say, okay, well, 1 minus 0.63 is going to give me P. And so that's going to give me 37. So since I know my P, I can find my P squared. So I'm just going to take P and I'm going to square it. So 0.37 squared is going to give me 0.136, or you can kind of round that, make it 0.14. And then to find my 2PQ, you can just sub in 2. Then sub in your P of 0.37, and then sub in your Q of 0.63. And that's going to give you 0.4662. Now, I always tell my students you want to check yourself. You want to check your math, make sure it all works out. So if I add 0.14 plus 0.47 plus 0.40, what does that give me? Well, it's going to give me 1.01, but that's due to a rounding issue, okay? So because of me rounding my extra decimals here is how I ended up getting this extra part, but that's going to be okay. So this shows me that I calculated it correctly. And so the question is going to ask you how many of them are homozygous recessive. And so you could look and say, okay, well, there's 40% that are homozygous recessive. How many of them are homozygous dominant? There's 14% that are homozygous dominant. How many of them are heterozygous? There's 47% that are heterozygous. And you can get all of your answers by looking at this one chart. So I always tell my students to solve the chart and then figure out what they need to answer. So again, when we solve this, we first started with Q squared. After we found Q squared, we moved over here and we did our Q. After we did Q, we then solved for our P. Then we found our P squared. And last but not least, we found our 2PQ. We found our Q by taking the square root of Q squared. We found our P by doing 1 minus my Q, which gave me my P. We found my P squared by squaring my, my P value. And then we found 2PQ 2 different ways. One, we subbed in our P and our Q. And the second thing we did was we added up these 2 values. We could have subtracted from 1, and that would have also given us our 2PQ. So that is one example that we could do. Another example that we have is where I'm kind of flip the switch on you a little bit, okay? And in this question, it tells you a very large population of mice contain 65% black mice. White is caused by recessive allele. So what they did is they gave you the dominant trait, okay? So that black is actually looking at both P squared and then also 2PQ. So we need to first solve for white. So if I know that 65% are black, okay, then that allows me to say, okay, well, my Q squared is going to be 0.35. And now I should be able to fill in that chart that we did a second ago. I know my Q squared is 0.35. So if my Q squared is 0.35, then that tells me that my Q is 0.59. My P is 0.41. my p squared is going to be 0.17, and my 2pq is going to be 0.48. Solving the exact same way we did before. Okay, and again, if you want to double check yourself, add these all together, that equals 1, and of course we solved this by doing the 1. So I didn't want to show you guys all the math, but if you need to, remember that to get to here, we take the square root of 0.35, which gave us 59. We did 1 minus 59, which gave us 41. 41 squared, which gave us 17. And then we did 2 times 41 times 0.59, which gave us 48. So that is how you would actually use Hardy-Weinberg's equilibrium formula. Now, there's a couple problems in which they want to throw a little kind of change at you, okay? And when they do this, they're going to give you the number of individuals that are each of them. So for example, here's AA, so that would be my p squared. Here I see AB, which would be my 2pq, and then here I see BB, which is my q squared. In this case, since they tell you the number of individuals, you have to use that in order to solve it, okay? So if I wanted to find my p squared, I'm going to take the number of individuals that are AA divided by the total. So if I look at the question, it tells me that there's 6,840 individuals that are AA. So I have to sub that in, 6,840, and I divide by 10,000 individuals because there are 10,000 individuals in total. And that is going to give me 0.684. If I wanted to find my 2pq, you're going to do the number of individuals that are AB divided by my total. So that told me that there was 28,600. I'm sorry, 2,860 divided by 10,000, giving me 0.286. And then my q squared is going to be my number of B's divided by my total. Look at the question. It says there's 300 individuals that are BB, and I just realized that you can't see the question, so I'm sorry, guys. So 300 individuals divided by our 10,000 gives us 0.03. And you could add all the zeros if you want, okay? And to verify, this, of course, adds up to 1. So we have, of course, we're meeting our Hardy-Weinberg, okay? We have 100%. Now, here's where life gets a little complicated. If I wanted to solve for the P, I need to find all of the A's. Okay, so what's the frequency of A? So if you look here, there's 2 A's in this individual. So there's 6,840 individuals that have 2 A's. So I'm going to take 2 times 6,840, and I'm going to add in the number of individuals that only have 1 A, because 2,860 individuals have 1 A and 1 B. So I do 1 times 2,860. And so if I solve that out, that's going to end up giving me 16,540. Okay, so you're going to divide by the total number of alleles. So before, again, we were told by the total individuals. Now we're doing it by the total alleles, which, since I have 10,000 individuals, that's going to be 20,000. So when I solve this, which I ran out of space, A is going to equal 0.827. So you could actually round that to 0.83. If you wanted to take the shortcut on this, you could say that B is just going to be 1 minus this value, so 0.17. But you could also solve it, and I'm going to grab another piece of paper so we can solve it to make sure that that actually is the correct value, because I ran out of space on my paper. So if I wanted to find my Q, which is my B, I'll do 2 times the number of individuals that are BB. So it says here that there's 300 individuals that are BB. So we're going to do 2 times 300. And then we're going to add in the number that are capital A, little b, capital AB, and that's 2,860. Add it together, and you're going to get 3,460 divided by the total number of alleles, so 20,000, which tells me that we have 0.173, which matches up with my 1 minus value that we had right here. So I'm going to look at the chat real fast and see if there was any questions, and then I will log it off. So can I save this live? Yes, I'm going to save the live. No worries there. There's no questions. So I hope that was helpful, and I hope you guys have a wonderful night. Bye.